Thanks, Matt, for sharing the good news with everyone. I'm really happy, so I want to share this happiness with all of you. The title of my talk is The Polytope of All Matroids, period. Actually, there is a period in the schedule if you look. Yeah, this is a paper that I'm writing right now with Alex Fink. Alex is at the moment at the Institute for Advanced Study, but he's regularly affiliated with the Queen Mary University of London. So I hope some of you have already read works by Alex. He's a great mathematician. We hope that this paper will be on the archive maybe next week or within the next 2 weeks. So even though it is in progress, it is almost ready. And yeah, since this is a very heterogeneous audience, let me recap what is a matroid. So in case you have encountered matroids before, for instance, as in Oxley's book, a matroid is a family of subsets of a finite set satisfying some nice property. If you want to be very precise, the condition is that, well, first of all, you have a finite set E, which is often called the ground set. I typically denote the set E with the square brackets n, meaning that my set consists of all integers from 1 up to n. And the collection that defines the actual matroid is called B, and it consists of a family of sets such that this exchange axiom is satisfied. I won't be using this too much for the talk, so I will just mention it in case you have seen it before, or if you are scared about what matroids are. The definition is very simple. But there is a polyhedral definition that I think many of you will prefer or will like more. So a matroid can be seen as a polytope such that it satisfies two conditions. The first is that the polytope has coordinates 0 and 1. So the vertices have coordinates 0 and 1. And the second condition is that all the edges, all the one-dimensional faces, are of the form EI minus EJ for some canonical vectors EI and EJ. So yeah, the second is a cryptomorphic definition of matroids. So if you tell someone, consider this class of polytopes, you are actually considering all matroids. So you don't lose anything in this using this alternative definition. So one way of building the polytope out of the classical definition is as follows. So you give me a matroid M, so you give me the ground set E and the collection B, and you will consider the convex hull of all vectors EB, where EB is essentially zeros and ones according to whether the element I, denoting the ith coordinate, is or not in the set B. Then you take the convex hull and you will obtain the matroid polytope that I just mentioned. And what you have to have in mind is that the vertices of this polytope P of M are just encoding the basis of the matroid. Questions so far? Okay, let me move on.
The edges are the exchanges.
What, sorry?
The edges that you mentioned, are they the exchanges?
Are the symmetric exchanges, that's right, yeah. You can prove if you are given the original definition or even the polyhedral definition that whenever you have two bases, they have the same size, and that size is called the rank of the matroid. I will be denoting the rank of the matroid in this talk by the letter R. And well, since all the bases have the same cardinality, all the indicator vectors have the same sum, which is R, and therefore my polytope will be living in this codimension 1 space in this hyperplane, which is given by all vectors that have sum of coordinates equal to R. A matroid is said to have C connected components if the dimension of this polytope is the size of the ground set minus C. So you are connected means that you have only one connected component, so the dimension is exactly n minus 1. So the only smaller space that contains your matroid is precisely this hyperplane. Okay, so now, a special class of matroids. This is very combinatorial. People knowing about various other aspects of matrix theory might have encountered these objects under various names. So just in case, these have names, alternative names such as generalized Catalan matroids, nested matroids, shifted matroids, freedom matroids, and among many others. I I will stay with the choice of Schubert matroid, which in my opinion is the best name for this object. And they are defined by using lattice paths, let's say. Or one of the many definitions that you can use is using lattice paths. So let me consider, as usual, the size of my matrix is n and the rank is r. Let me consider like paths that go from 0, 0 to n minus r, r. So I will consider northeast lattice paths. So my admissible steps are of the form go one step up or go one step to the right. Diagonals are not allowed. So, well, take any path of that shape. For instance, I have drawn one highlighted black path here. And then record the positions of the steps in which you went upwards. So here, you can see this path U, and you can see that I went upwards in the first step, in the second step. Then the third, fourth, and fifth, I did not go upwards. So I will skip 3, 4, 5 from this list. And I will continue. So we'll have one set U. Well, I can do that for every lattice path. So whenever I have a fixed one, let's call it U again, I can consider the set of all lattice paths that lie strictly below U. Namely, that they do not cross U and go above. If you consider the set B, given by the collection of all these paths and listed in this way, you will end up with the set of bases of a matroid. That's not trivial, but not hard. So maybe if you are teaching a course in combinatorics, you can ask your students to prove that this indeed defines a matroid. And well, what's a Schubert matroid? A Schubert matroid is any matroid that is isomorphic to one of these objects. So you can find some lattice path such that if you do the construction that I just showed you, your matrix is isomorphic to this one.
Catalan numbers are a special case. Do we know that matroid?
Yeah, I mean, there's a class called Catalan matroid. So first observation, so if you have two paths that are not the same, then the Schubert matroids that they induce are non-isomorphic. So in particular, you can see that since there are n choose r different paths, you can have n choose r Schubert matroids on n elements and rank r, two of which are isomorphic. So there are exactly n choose r isomorphism classes of Schubert matroids of size n and rank r. Actually, this was related to a question that someone proposed, I think on Monday, related to the enumeration of positroids. So there are n choose r isomorphism classes of Schubert matroids. This doesn't say anything about how many Schubert matroids there are. So Schubert matroids are things that are isomorphic to these things. So the labeling will matter. And in fact, we will see later that this enumeration of labeled Schubert matroids is slightly more tricky. One comment, not all matroids are Schubert. For instance, if you take the direct sum of two uniform matroids, so if you know about graphic matroids, so you are taking the direct sum of two pairs of parallel edges. So if you do that, then the resulting matrix is not Schubert. And in fact, among the matroids on 4 elements and rank 4, there are 7 isomorphism classes, 6 of which are Schubert, and 1, which is this U12 plus U12, which is not. So the morals is that Schuberts are nice, but they are restricted class. So not all matrices are Schubert. Yeah.
Dumb question here, but what would like the bases be for this Schubert matroid in terms of like the lattice path you've drawn out?
For which matroid?
Or,
for
yeah.
Choose whatever Schubert matroid in this list that you like. For instance, I don't know, this one.
Sure.
So your upper steps are 1 and 2. So you will take. So for the highlighted path, the upper steps are 1 and 2, and actually every lattice path stays below. So take whatever set of size 2 that you like, and it will give you a path that stays below the highlighted upper path. So this will be the uniform matrix U24. So everything is a basis.
Gotcha.
And in this case, in the first case, you will have the matrix U02 plus U22. So 2 loops and 2 co-loops. Yeah, and I think that. Yeah, it's not difficult to show that, for instance, this matroid, the fifth one in this picture, is actually a graphic matroid. If you want to see it, it's something like take a triangle and duplicate one edge. So yeah, not all matroids are Schubert, but yeah, as we will see, Schubert matroids are very important for the construction I'm going to tell you about today. So first of all, let me go back to the geometry of matroid polytopes or polytopes in general. So I will define the indicator function of a polytope or a subset of R to the n in the following way. I will use the overline, which is very annoying. I didn't want to use the overline, but it's the best choice for you will see later. So this one overline is a function that returns 1 if the input is in the set X that you are given originally, and 0 otherwise. So this is giving you 0 or 1 according to whether your points lie or not in the set X that you're giving at the start. And this is one reason that the overline is important. I want to define something that doesn't take into account the choice of the coordinates in R to the n. I want to have all permutations like being the same, all labelings of the coordinates being the same. So I will define the symmetrized indicator function, which is one without the overline, in the following way. If you give me a set and at some point small x in R to the n, I want to take 1 divided by n factorial and sum all these one overline over all ways of permuting the coordinates of the point x. Is it clear what I'm doing here? What you have to remember is the good indicator function is the one with the overline, not the. And yeah, the reason for that will be clear in a moment. Yeah, what you can conclude from this definition is that if you give me 2 isomorphic matroids, well, the embedding of their polytopes will matter, so I will have 2 different indicator functions, though the symmetrized indicator function will be the same thing. So I am trying to essentially identify stuff by doing this game. Okay, so key notation and the overlines and the not overlines are really important, so let's be very precise. MRN and SRN without overlines will denote, respectively, the matroids on this ground set of integers from 1 to n of rank R up to isomorphism. So in this MRN, I have all the isomorphism classes. And in SRN, I have the n choose R isomorphism classes of Schubert's. Okay? And I will put bars when I do not want to identify isomorphic stuff. So M bar Rn will contain all matroids. Also, there will be many copies of the same matroid up to isomorphism. And the S bar Rn will be all Schubert matroids. So just so that you know, the number of Schubert matroids is n choose R. The number of matroids up to isomorphism is an open problem, even asymptotically. And the same happens here. It's we do know what SRN bar is. It's related to the H vector of the stellahedron, if you know what that is. And this M bar is very hard and also not known, not even asymptotically. So yeah. Question so far? Okay, so now that I showed you these indicator functions, I want to define a special class of functions on the space of matroid polyhedra. Give me any abelian group that you like. For instance, a set of integers or a set of univariate polynomials in the variable x over the reals, whatever you like. And yeah, we will say that a map taking a matroid and returning one element of this abelian group is a valuative function if whenever you have that this integer combination of indicator functions is the identically 0 function, then the corresponding combination changing the 1 overline Pm by just f of m, this is 0 in the abelian group. So what I am asking is that my function f factors through the indicator functions with the overline, and this is to be a valuative function. It is a non-trivial theorem. Actually, this is not true if you take an arbitrary class of polyhedra, but it is true for matroids and generalized permutohedra, that this is the same as requiring that your f behaves as a measure under subdivisions. So what this means is that if you take, for instance, a matroid polytope given by the full octahedron, f evaluated in the full octahedron has to be the same as evaluating f in the top pyramid, which is a matroid, f in the bottom pyramid, which is another matroid, minus the common intersection, which is, again, a matroid, is this square. So, yeah, it's not quite the same. So if you take functions that behave inclusion-exclusion-wise under subdivisions, and you take functions that factor through indicator functions, you might believe, oh, these are the same kind of things. Well, no. You have to take a look at McMullen's work to see like the hierarchy of things that you can define in this vein. And yeah, the thing is that for matrix, these two things are equivalent. So yeah, whenever you see valuation, you can think in either of these two senses, and it will be correct. Now, a valuative invariant. So let me assume that f takes the same values on isomorphic matroids. So before, I did not assume that. You could give me the two pyramids, and f in the top and the bottom could be different things. But now let me assume that f will take the same values on the isomorphic matroids. Then that leads to the notion of valuative invariant. So what I am changing with respect to the previous slide is that instead of valuative function, I'm writing valuative invariant. Here, instead of the overline, I am just using the symmetrized indicator function. And for instance, here, instead of having the relation like f top pyramid plus f bottom pyramid, I can just write 2 times f of the top pyramid because, well, I am assuming that, yeah, I mean, on isomorphic matrix, I'm taking the same values. Questions? Everything okay? Okay. Okay, so now we're facing what I regard as the most important theorem connecting Schubert matroids or the main reason why Schubert matroids are very important. So this is by Dirksen and Fink in 2010. If you give me any matroid, whatever matroid you like, and you consider this indicator function, then there is exactly one way of writing this indicator function as an integer combination of indicator functions of Schubert matroids. And of course, all these Schuberts have the same rank and cardinality as your original matroid. And of course, you can symmetrize everything, and you will get that every symmetrized indicator function can be written uniquely as an integer combination. Notice that here, this AS prime will be, in general, a sum of these AS that you have on the first display. So yeah, the thing is that independently of the matrix you are giving me, I will be able to find this decomposition in a unique way. And the coefficients of this decomposition are integers. Well, this is the key result that will enable us to build the main characters of this talk. So let me define the polytope of all matroids. So if you give me a matroid M, so here I'm taking any matroid, I don't care about the labeling. Well, this will give me a unique point, P of M, let's be very precise here. So I have one integer coordinate per Schubert matroid. So this is a huge vector having Schubert many coordinates. And I will put as entries the AS's that I showed you in the previous slide, which are uniquely defined. And then I will do that and take the convex hull in R to the Schubert and R. Is it clear what I'm doing? Okay, you can do the same game, but up to isomorphism, and you will end up with another polytope. Notice that the polytope of all matroids is omega over line Rn, and the polytope of all matroids up to isomorphism. Here I have omega Rn. Here I have a typo. I should have switched N and R. But yeah, the thing is that without the overline, you are considering isomorphism classes, and with the overline, you're considering everything. So all labelings are different things. Okay, so let me give you an example. So yeah.
I think I missed something. You said that not all matroids are Schubert, but they all have this Schubert expansion?
Exactly.
Okay.
Yeah. So for instance, if you give me a Schubert matroid, this decomposition will be 1, 1, and zeros everywhere else.
Does every lattice point in the hull mean something?
You will see that addressed in maybe slide 20 something. Yeah. Okay, so let me do one example so that you can see what this is. Let me do omega 2, 4, like without the overline and with rank 2 and 4 elements. I already showed you that there are 6 Schubert matroids. So if you want to write each of these 6 Schubert matroids as a combination of Schuberts, you will obtain that, well, like the first should be something that has 1, 1 and zeros everywhere else, and the same for the second, and so on. But you have to do it for all matroids. So you are still, I mean, you still need to do this for U12 plus U12, which is the only non-Schubert matroid on 4 elements and rank 2. If you like compute it, like maybe by hand or using whatever fancy theorem on matroid theory that you like, you can compute this, that the symmetrized indicator function of this matroid is essentially twice the symmetrized indicator function of this Schubert matroid minus 1 time the symmetrized indicator function of this Schubert matroid, which that's the uniform. And yeah, if you label like these 6 Schuberts with the numbers from 1 to 6 and like write the coordinates using this ordering, well, like this matroid will be 1, 0, 0, 0, 0. This will be 0, 1, and zeros everywhere else, and so on. And this U12 plus U12 will be zeros everywhere, 2 minus 1. You have to take the convex hull of all these column vectors, and there you will obtain the polytope of whole matrix omega 2, 4. You can see that, yeah, this will be a simplex.
Luis?
Yeah.
I missed that, but also for the symmetrized indicator function, the coefficients are integers?
Yes, yes. For symmetrized indicator functions, they are integers, and they are sums of some complicated sums over the coefficients of the original one. Yeah, yeah.
Does uniqueness mean it's always a simplex?
No, the geometry is very complicated. So yeah. But
There's another
yeah.
question.
Sure. Yeah.
I'm sorry if I missed it. You ordered your Schuberts. Why that order?
Because
Arbitrary?
yeah, I mean,
Okay,
to be very precise, I am always like thinking that my Euclidean spaces are to the Schubert matrix. so my coordinates are labeled by Schuberts, not by numbers. But in order to draw this matrix, I don't want to like. I mean, I want to use numbers so that I can tell you the polytope easily.
I was just curious if there was like a special way that I should order the Schuberts.
No.
Like, because if I drew it, maybe mine weren't the same order.
If you change the ordering, you will obtain something that has the coordinates permuted. So, yeah. Other questions? Okay, so this is omega 2, 4. Okay, so basic theorem, like the first thing you can ask, well, what's the dimension of this thing? Well, theorem, the polytopes omega nr and omega bar nr have codimension 1 in their ambient space. So they are living in some R to the Schuberts or R to the non-isomorphic Schuberts. Well, in each case, they have codimension 1. That means that they lie on a hyperplane, if you want. What's the idea? Well, I mean, you can see from the previous slide that, well, all Schuberts are themselves matroids, so I will see always like the vectors 1, 0, 0, where the 1 is in every possible position. They will appear. Yeah. And then you can use a very nice result by Felipe together with Alex and Federico Ardila, in which they show that constant functions are valuative functions on matroids. That's also non-trivial, even though it's very simple. That requires a topological reasoning on matrix subdivisions. So if you use these two things, you will conclude that whenever you have any matroid, you take the Schubert decomposition, the sum of coefficients is always 1. So yeah. So in particular, all the points in these polytopes will live on a hyperplane, sum of coordinates equal to 1. And you can show that because like you have like all these Schuberts that are like essentially linearly independent, you will have always at least like dimension space minus 1. Now, you can tell me with this reasoning what's the dimension of omega 3, 6. Well, there are 6 choose 3 Schubert matroids, and I am losing 1 dimension, so I have 20 minus 1, so I have dimension 19. So already for small values of the parameters, this has its dimension very large. This, the one with the overline, instead, I mean, I am not identifying Schubert matrix, so I have many more things. Well, if you compute this number, it's 882. So the dimension is huge. If you are interested, so this is like the third Betti number of the sixth stellahedron. If you know what that is, great. Otherwise, I can tell you a formula to compute these things in terms of Eulerian polynomials. So yeah, it is known how to compute the dimension in a closed form. But it's not easy, let's say. Okay, remark. In the labeled case, so in the polytope omega bar Rn, whenever you give me two matroids that are not the same matroid, then they will give me different points. And the reason is that, well, if you give me two different matroids, I mean, the indicator functions cannot be the same. So yeah, if they were inducing the same point, the indicator function would be the same, so I will have the same matroid. So that's essentially like a trivial thing to check. But if you give me two isomorphism classes, that's no longer true. You can have two isomorphism classes, say bracket M and bracket N, that are different, though the point that they induce in R to the S Rn without the overline, they are the same thing. So you can have isomorphic matroids having the same symmetrized indicator function. So one has to be careful with that. And because of that, one expects the polytope omega Rn to be much more delicate than the one with the overline. The one with the overline is like essentially all points come from different matroids. So essentially, whenever you see a lattice point here, you expect it to come from a set of matroids or a set of isomorphism classes. The vertices. I told you the dimension. What are the vertices? Well, the vertices of the thing with the bar are boring. All the matrices are vertices. Okay, even though that's a simple statement, the proof is not super easy, but still I can tell you the ideas. So what's a vertex in a polytope? Well, a vertex in a polytope is a point that is a single maximizer for a linear functional on the ambient space. And by Dirksen and Fink's result, the linear functions in the ambient space of omega bar Rn are precisely the valuative functions. So essentially, if I want to prove that something is a vertex in the labeled polytope in omega bar Rn, what I have to do is you give me a matroid, and I have to cook up some valuative function that is maximized only at your matroid. How to do that? Well, one way is the following. So you give me the matroid M, and I cook up the following function, Gm, that does the following. If n is the input matroid, I want to compute the number of bases in common and the number of non-bases in common. So if you do this, well, you can prove that it is a valuation. That's not super easy, but doable. It relies, again, on a paper by Felipe, Alex Fink, and Federico Ardila. And yeah, you can see that this quantity is always at most n choose r, and the equality is attained only if n equals m. So that proves that whatever matrix you give me is a vertex. Questions? Okay, so I told you the vertices of the labeled polytope. Now let me move to the vertices of the unlabeled polytope. So observation, remark, not all isomorphism classes will be vertices. So this polytope is much more interesting. So let me define a new notion, which is called being extremal. A matroid M is said to be extremal if the point P sub bracket M, so the isomorphism class of M, is giving me a vertex of the unlabeled polytope. Okay, what's the smallest non-extremal matroid? Well, it's this Schubert matroid here, which you can check by the previous computations that I did in the previous slides, that it is the midpoint between the uniform matroid U24 and U12 plus U12. Since it's the midpoint of two matroids, it cannot be a vertex. yeah, so this graphic matrix is the smallest non-extremal matrix. And okay, let me tell you one reason why this polytope, omega Rn, is like, in a sense, a fundamental object to look at. Extremal matroids can be used to disprove conjectures. So what type of conjectures? Let me argue about that. So let's assume that F is your favorite valuative invariant of matroids. For instance, you can think of the Ehrhart polynomial of the matroid polytope. You can think of the following quantity defined in terms of the Tutte polynomial. You can think of the Cash and Lustig polynomial of a matroid, or the Spires G polynomial, if you know what those things are. Or, in fact, almost anything reasonable that you can think of about matroids. It's very surprising, but whenever you come up with some reasonable invariant, it will be evaluation. Of course, if you take the square of the Ehrhart polynomial, that's not reasonable. So that's not evaluation. But the Ehrhart is reasonable, and that's evaluation. Yeah. Let's assume that you want to formulate a reasonable conjecture on your favorite valuative invariant F. You want to conjecture that F is non-negative for all matroids. Yeah, question.
I have a question. Can you explain why Ehrhart polynomial of the matroid is invariant? What does it?
Well, the thing is that the Ehrhart polynomial is invariant under permutation of coordinates. So if you give me any polytope that you like, and you permute the labeling of the coordinates, the Ehrhart will stay the same, because permuting the coordinates is a unimodular equivalence, if you want. Okay, so you have this reasonable conjecture. So someone has given you their favorite valuative invariant F, and is conjecturing that this is true. I mean, in all these cases, there were conjectures of this form. Okay, lemma. This is a one-line proof, so this is just a lemma. But the reasonable conjecture is true if and only if it is true on extremal matroids only. So you only have to check extremal matroids. And if you believe in a very long-standing conjecture in enumerative combinatorics that is expected to be true, then 0% of matroids are extremal. So you have very few things to check. What do I mean by 0%? Well, that if you enumerate extremal matroids on n elements on rank R, and you enumerate all matroids on n elements on rank R, this quotient will be close to 0 for large n. Like that's the statement. And the conjecture is actually due to Giancarlo Rota and Henry Crapo. So, yeah. The conjecture claims that essentially 100% of matroids are sparse paying. That's yeah. And I will argue in a moment why essentially that would imply this phenomenon. Like, so the motivation in the end was to have parameter polytopes for counterexamples in matrix theory. So study counterexamples. Give us some good framework to study counterexamples. And this is a good framework in my opinion. So I want to tell you a few examples of extremal matroids because I have not done so far. So as I said, vertices are things for which the linear functionals attain global maxima. So you can prove using that approach that the following matroids are extremal. Uniform matroids are extremal. How do you prove that? Well, take the valuation given by number of bases. So if you compute among all matroids on n elements on rank R, the one with the most bases, well, it's this guy. So this is a vertex. If you compute among all the matroids on n elements on rank R, the one with the least amount of bases, it's this guy, a bunch of loops and co-loops. So yeah, only one basis here. Remember that in matrix, I'm not allowed to have 0 bases. Now, take uniform matroids and now duplicate every edge in parallel. Well, that's another extremal matroid. And let me give you another example. If you know what sparse paving matroids are, great. If you don't worry about this. But all sparse paving matroids coming from maximal stable subsets of the Johnson graph, all of those things are extremal. And why I chose this list of examples? Well, because precisely these duplicated uniform matroids yield counterexamples to the Merino-Welsh conjecture. So in the previous slide, I showed you this quantity. So people have conjectured that this was non-negative for all matroids. And this was disproved last year by Beckett, Saji, Sigbari, and Pituc. And they used precisely these matroids. And yeah. And the last example was used by myself during my PhD thesis as a tool to disprove a conjecture by the Loera, Haws, and Köppe on the Ehrhart positivity of matroid polytopes. So yeah, I guess that you can see that indeed extremal matroids in practice will give you counterexamples if you are able to find some. Okay, so let me leave you a few conjectures that I think are very relevant, and then maybe they are doable in the sense of, I mean, spending enough time, you will be able to crack them. I have tried, but I failed, but that doesn't mean anything. I didn't try everything, so yeah. First of all, I conjecture that if you take a complete graph, well, that induces a matroid, well, I conjecture that matroid will be extremal for all n. And more generally, if you give me a complete multipartite graph, that will be the case as well. So a complete graph is a complete multipartite in which each part has size 1, so it's a particular case. And we have similar conjectures in the paper about projective geometries and truncations of projective geometries. You can ask me whether certain operations preserve extremality or not. And unfortunately, the property of being extremal is not closed under minors. So you won't be able to characterize all extremal matroids by saying, forbid this thing. That's just not true. You can prove, because it's clear, let's say, geometrically, that the polytope of all matroids omega Rn is isomorphic to the polytope omega n minus Rn. So in turn, that is saying that a matrix is extremal if and only if its dual matrix is extremal. So duality preserves extremality. Questions so far?
Is there a simplex method for taking a valuation, finding an extremal matroid from a starting matroid and mutating it?
Great question. I don't know. If that's true, that would be amazing. Like, in fact, I'm having trouble to actually compute these polytopes, especially the one with the bars, because dimension goes huge, like super fast. So there are a few things that I just cannot check with my computer. I need some big cluster or something. Okay, theorem. This is one theorem that is very neat, though it is particularly tricky to prove. If you give me a direct sum of matroids, and this direct sum is extremal, well, then each summa that you gave me was extremal. And we conjecture that the converse is also true, so that if you give me S extremal matroids, and then the direct sum will be extremal as well. So direct sums and extremality behave well within each other. And yeah, we expect that some hop theoretic structure of matroids will play a role in the proof of this conjecture. Alex has tried for maybe 2 months to prove this. I tried a little bit less, but this is hard. I mean, or at least this is from, I mean, in my opinion, this is one order of magnitude more difficult than the previous conjecture. Yeah.
What's the relation between the vert or the lattice point associated to the m's and the lattice point of the sum?
That's part of the difficulty. Yeah, that's part of the difficulty. If we understood that a little bit better, that would be amazing. But we don't. Yeah. Okay, so I want to tell you a few things about the faces. So I told you about the vertices, but the vertices are just the zero-dimensional faces. So you may ask about other faces. Well, one reason why these polytopes are not that crazy is because faces of the polytope are essentially classes of matroids. So, example, paving matroids are a face of the polytope. They will form a face of dimension n minus r. So all these computations of dimension are non-trivial. So whenever I say a number, it's not obvious that it's that number. You have to do something which takes some work. So paving matroids form a face. That is relatively easy to see. The dimension counting is not so easy, but you can prove that paving matroids form a face of dimension n minus r in this polytope, and this complicated sum in the labeled polytope. Sparse paving form a face of dimension 1, and that is pretty surprising. So it's an edge of the polytope omega Rn, and dimension n choose r in the labeled thing. So yeah, you have an edge that is sparse paving. So you can ask me what are the two vertices that edge the limits. And one is the uniform matroid, and the other are those that I mentioned on the stable subsets of the Johnson graph. So you know what the vertices are for that edge. Yeah, elementary split matroids, these were defined in tropical geometry by Joswing and Schroeter. Those also form a phase. The dimension is, let's say, symmetric in the sense of it's r times n minus r, so it's slightly nicer than paving, let's say. And the computation here is, well, horrible for the labeled polytope. And simple matroids also form a phase. The dimension is n minus 2. Choose r minus 2 minus 1 in the labeled in the unlabeled polytope, and I mention some entry of the Chow polynomial of some uniform matroid. I can be very precise about that, but I didn't want to write it because I don't know. I mean, it's too early. I mean, it's maybe in the evening I can write it. Yeah, this is a horrible number. Like it will involve Eulerian numbers and Chow rings of matroids and whatever. But you can compute the dimension of simple matroids in the labeled polytope. Disconnected matroids also form a phase, but we don't know the dimension. That's an open problem. I have no clue, and I presume this is super hard. You can prove me wrong. Okay, so lattice points of the polytopes. That was a question that appeared early in the talk. Well, theorem.
Question.
Yeah.
Briefly, in the previous slide, I don't understand what you mean an edge. So all of them are in a very long edge?
Mm-hmm. In a sense, you will see all of them in a very long edge, but remember that some things can collapse to the same point. So what will happen is that you will have the uniform matroid. There's only one labeling for a uniform matroid, so that's a single matroid. Then sparse paving, you will have many things that are like different matroids, but the same isomorphism class of matroids that give the same point, then the same here, until you will reach one point that is like the one coming from the extremal stable sets in the Johnson graph.
But how does this relate to the fact that you say that most of them are not extremal?
Well, because all of them will fall into an edge, so those cannot be extremal. So the conjecture is that all sparse paving are, almost all matrices are sparse paving. So what I'm saying, well, but all of those fall into the middle of an edge. So
I see.
yeah.
So there'll be a supporting hyperplane, it just won't be a vertex.
Yes.
Yeah, exactly.
Do you know what it is?
No, I have not computed it, but maybe one can do that, yeah. There was Ben? Yeah, no? Okay, so the lattice point thing about these polytopes. So first of all, not all lattice points in this omega without the overline come from matroids, and that's pretty annoying. Remember that the polytope omega without the overline is expected to be much more delicate. Yeah, but for this one we can run computations because the dimension is smaller, and I found these 5 points, none of which come from a matroid. So you can check with your favorite software that this is true. I don't know how to prove this in the paper without like saying, use the computer. The question that I regard as the most fundamental question about this polytopes omega bar Rn is whether all points in these things come from matroids. I have not been able to find any counterexample to that, so it might be the case that that is true. And that would be maybe one reason why this polytope is also very important. I have emphasized the one without the labeling, and that's why I did not put the labeling on that one. But yeah, also in this one we have like this open problem. And this is something that maybe one can do with some smart coding on a powerful computer. So if you like computational problems, this is a good one. And finally, let me comment briefly on a more, let's say, theoretic question that, so there's right now there's a special program running at the Institute for Advanced Study on matroids and Hodge theory and things like that. And well, there are many questions that have to do with proving that some invariant satisfies some positivity property. And the yoga there is more or less as follows. You prove it for all matroids that are realizable over a field of characteristics 0 using presumably some algebra geometric tools. Then you prove it for all realizable matroids using some version of the algebraic geometry in the characteristic 0 case. And then you develop some new machinery that mimics the algebraic geometry for the general case. A folkloric question that many people have asked throughout the years is whether you really have to do all these steps. So the question is this. If you know that something is valuative and positive for all realizable matroids, can it possibly not be positive for matrices in general? And I challenge you to try to construct some valuative invariant that is non-negative at all representable matroids, but fail to be non-negative in general. You will very quickly realize that that's very hard to do. But in the language of these polytopes, well, we can prove that the answer is yes, you can find valuative invariants satisfying this property. And notice that this is saying that you can find valuative invariants that serve as representability tests. So there is some valuative invariant that has that property, that it evaluates to something positive for realizable matroids, but negative for non-realizable. It's not it's a test, it's not a characterization. Let me be very precise. And the idea in the language of the polytope is to construct some non-realizable extremal matroid, and the smallest that we have been able to produce has 19 elements, so pretty big. So these are polytopes on dimension 18. So this is hard, and proving that those things are, extremal is hard and non-realizable is hard, because how do you prove that something is not realizable? You have to argue, taking some candidate of the representation and see that something breaks, and that is often very hard. Let me finish here, and that's all.